Yes, sir.
Okay, for circular motion. For circular motion, yeah, like for circular motion, there are 1, 2, 3 important points over here. Okay, so apex angular displacement. I think this one you already have mastered. Apex angular displacement in radian, define velocity and period. I think this one you have done it. Derive the formula. Derive formula is this part. Okay.
Sir, the one is blur a bit, sir. The writing can't see.
Which
Blur.
one?
The writing, the screen is blur, sir.
I think our screen is blur.
Yeah.
How about now?
Okay, bit, sir.
This one I already gave
yeah,
to
okay,
you.
sir.
I already gave to you, Abi.
No. Then SEM 2 you got give, sir. Yeah. Got. SEM 1 got.
So like express angular displacement. This one we have done before. Okay. Angular displacement. This one we have done before. Angular velocity and period done. Use the derive formula. This one jadi I don't know either you will be asked or not. Okay, I think it has been asked before. There are two types. One is you have to draw. One is can you see on the screen?
Yes, I can see.
Okay. One is S and R. So it is called as geometry. The what call the length because of geometry.
The arc, sir.
The arc because R and S is geometry. One more is because of the vector. This is vector. So one is length, one is vector. Vector, you see the geometry we only has R. Of course, R1, R will be same on top and the bottom will be same. And the S is the we call the arc because of the R, right? And S equals to R theta or one more, the theta over here. And this theta will be same over on the vector diagram. So vector diagram has V A over here pointing on the right. You can see over this side B, and VB pointing towards downside, and minus over here. So VA change of V equals to VA minus VB. So you can see that is I can see if I draw another color, VB by vector. Okay, this is a vector in maths. So this is VA. It's the same color. VA. Okay, this is VA. And then between them is actually it's not like that. It's a bit towards down here. So this one will be V change of V. Okay. So by the head and the tail of the vector, this one pointing down, this one pointing this way. Okay, you can see that change of V is actually VA minus VB. Okay. Yes or not? Because the VB actually pointing here. If VB pointing up here, so change of V equals to VA plus VB. Or we can say that you can see the head and the tail pointing up for VB pointing VA pointing here, and this one pointing down for change of V. Can you see that? You see the head of tail, head to tail, and head to tail. So this one is VA, change of V equals to VA plus VB. But because VB is pointing downwards this way. Okay, this way. So that's why change of V equals to VA minus VB. This is a very simple vector. This is in maths actually. Okay. So therefore, you can see that over here, okay, change of V over V and change of S over R. So that you have to combine these two by geometry and by vector. Change of the theta, okay, change of V over V, where is it? Change of V over V, where is it? Change of V over V. This is change of V over V. Okay. And equals to change of S over R, because both of them had the same theta. Left side and the right side had the same theta. So change of V over V equals to change of S over S, and this one equals to change of theta. So you can see that by geometry and by vector, both of them are related by the theta. Both had the same theta. Okay. So since centripetal acceleration A equals to, oh, this is, I think, hard for you to see. Make it bigger. Okay. So since A is V over T, okay, V over T, we have where is it? Change V over T. So have V equals to S over T. Where is it? One more here. You have to remind V equals to V over R times S. S equals to R theta. Okay. Where is it? And goes up. Change of V. Change of V. Change of V equals to change of S over R. So you have change of V equals to, this one goes up. So V over R times with the change of S. Okay. So change of V equals to S, this one correct. Since the centripetal acceleration is A equals to change of V over T. So we have to divide it by T. Okay, we have change of S over T. Change of S over T. Okay, just divide it by T. Okay, when you divide it by T, then you have V over R over here. Okay, so S over T. Okay, I know it. You just divide it by T, change of T, then you have change of S divided by T. So change of S divided by change of T. This is another thing. So V over R left with V over R, and S over T is a V actually, right? This is V. The whole thing is here is V. So V squared over R equals to R omega squared. Okay. Or we can use V over R. So expression is V squared over R. I think it's assuming that VA and VB is same. So that's why using V over here. It doesn't say VA minus VB. Okay, so we conclude that V squared over R or R omega. I don't remember, is it asked already in the STPM or not? Okay. By centripetal force, of course, F equals to MA. So m times v square over r. Okay. And the direction will be pointing towards the center of the circular motion. So if one thing is doing circular motion like that, the forces will be pointing towards the middle of it, center of it. Okay, now we have a horizontal circle. Okay, on the smooth table. So there you have F equals to T, the tension of the rope or the thread, equals to A, so V square over R, and R is the length of the string. Okay. So if an object is placed on the rim of the table, okay. So let's say an object is placed on the table with a friction between them. So this is a side view, mg pointing down, normal pointing up. So object has no vertical motion, n equals to mg. Okay. So the force that enables an object remain in circular path is force of static friction. This is static because no slip-ring occurs at point contact between the object and the turntable. The frictionless, the object will continue a straight line and slide off the table. Okay. So there we have a condition is F max equals to mu n. Have you learned conical pendulum before?
Yeah, sir.
Okay. So conical pendulum is you just make a free diagram. Okay. So pointing up will be T cos theta. This one will be the angle over here. T cos theta. Okay. So mg pointing down this way, mg, and the force, centripetal force is T sin theta. Okay, the theta is over here. Any question? Okay. If you have any question, you can ask directly before I go.
Sir, for the tension, right, sir?
Which one? Conical?
Yes, sir. Do we need to wait? I think okay, sir.
Okay.
No question.
So T sign over here, the tension over here, pointing to the right side, to the center of the circular motion. T sine theta is equals to the centripetal force, or mv square over r. Okay. So for conical, you also can find the speed. From here, you can rearrange v equals to change of Lg sine theta tangent theta. Okay, you can get from over here. Vertical circular motion, where as a Ferris wheel, it goes up and down. So this is a bucket pointing up, a basket pointing down. Okay, so it goes here. So at some time, the tension of the I don't know, wheel. Oh, it's not wheel. It's maybe a rod. Sometimes the tension of the rod is higher. Sometimes the tension of rod is lower. Okay. Oh, no, sorry. When it goes up at the upper side and the bottom side, at upper side the tension will be lower, and at the bottom side tension will be bigger. Okay. This is because of the acceleration of the circular motion. So if you can see that during the circular motion, okay, when at the bottom, okay, I think this is on at the At the top, the top, this one at the bottom. Okay, at the top, when the basket or any object at the top, the acceleration is pointing, this is top, acceleration is pointing down. So the mg also pointing down. So F, see this is a T, F plus T, because T has the same direction as the acceleration, F plus T equals to ma. At the bottom, okay, or we can say that T equals to mg. mg plus T equals to ma, so T equals to ma minus mg. Okay, T ma minus mg. So you can see that this is minus. For the bottom case, for the bottom will be acceleration pointing upwards, mg pointing downwards. Okay, so mg, oh no, this is T, T minus mg. Okay, T minus mg because T has the same direction with A, but mg has opposite direction with acceleration. So this one will be equals to ma. So T equals to ma minus mg. Okay, so you can see that it's it's a plus. So this side is a plus, so means that the bottom, the tension is higher. At the top, because it's minus, tension will be lower. You can see over here and this part there. Okay. Okay, example number 1, explain why particle moving circular path with constant speed as acceleration. Acceleration is change of velocity, because the velocity is a vector. Okay, and vector has magnitude and direction. Okay, so although the magnitude is same, you can see that magnitude is same in this case, v1 and v2, but the direction has been changed over here. So it is changing, and changing. Okay. Particle move position A. A particle move from position A to position B in circular path radius r with constant speed v in time t as shown in diagram below. Draw diagram to show the change of velocity. Okay, there you have VB. You have a V here, and change of V. Okay. Show the angle between the velocity at A and B is V change of t over r. From S equals to r theta and S equals to V change of t. So r equals to change of theta. So theta equals to V t over r. Okay. Derive the expression for the centripetal acceleration A in terms of V and R. So acceleration is V over R, or this is derivation. Okay. Okay, this is we have done before. A equals to change over V over T, and V equals to change of V times with the R. Okay, so this is again using the vector diagram. V is change of V, change of R. Okay, from S equals to R theta. So S is V. You can see S equals to R theta. S is actually change of V. R is actually V, and theta is a theta. So change of V equals to V change of theta, or V theta, right? From here you have V, and all of the thing divided by T. You just divide by T. and you have theta over t. Okay, we change of theta over r. Then you have, actually you can use above method also can be used, or this one. Same question. One more. The mass hang from the end of elastic string of strength L as shown in the diagram below. So it's assumed that this is a horizontal or vertical. It's a vertical circular motion. Up and down. Up and down. State the condition for the mass to reach the highest point of P. Okay. So the tension must be bigger than 0. Right. If it's lesser than 0, the thing will be wobbling up. It doesn't go up. It just falls down like that. Okay. So tension must be bigger than 0. That's the first condition. Deduce the minimum speed of the mass P in terms of U. So at P over here, we have done T equals to mg. We have derived this before just now. For minimum T equals to 0, so mg equals to mg equals to, or this one, 0, you replace in the T. So mg equals to mv over L. So v squared equals to gl. So another thing, we have conservation of energy, one part more. Half mvu mg 2l. Why 2l? Because it is height of 2l. And the p over here is a type the height of 2l. So 2l over here, that's why mg 2l and half mv squared. So u is square is 5v squared, and v is u over 5. Discuss the motion of mass if it launched from A with speed less than u. Launch from A. If it launched from A with less than u, the mass oscillate or the string slacks. The mass leaves the circle and move in a projectile path until the string becomes taut again. So it does not move in the circular motion. Example here, number 3, a level radius of track of radius 120 meter designed for the car moving at 80 km per hour. So we have a radius of track. This is 120 meter. Car moving over here with 80 km per hour. Calculate the minimum value of coefficient substitution between tires and track so the car does not skid. Okay. So velocity is 22. We have to convert to kilometer hour into meter per second. So it's 22 point. Okay. 22.22 meter per second. Centripetal force F. So frictional force equals to nu mg. Okay. So U equals to V squared over GR. Okay, so V 22.22 squared divided by 9.81 times 120, then you have 0.419. Okay, the minimum static friction to make sure the car does not skid. Okay, I think this is the whole thing of the centripetal. Any question? One more famous question is about, we have a disc over here that is rotates, and then we have a coin. Okay, given the nu of the coin, how much the static friction of the coin, and how fast is the turntable is the disc is rotates. Okay, this is O, is rotates. So find how much is the omega of the disc before the coin will be slippery. So from there we know that Fc equals to nu mg. So mv squared over r equals to nu mg. So m cancel. So or we can use m r omega squared equals to nu mg.
So
So yes,
so I need to minus by mg or
minus
the
mg
FC.
fc.
FC minus mg equals to ml.
fc minus mg. Why you want to minus? Okay, see, this
Because
is the side view. This is the side view, Abi. This is one with the coin, right? So mg over here. So this is the normal r or normal. This is the thing over here. So fc over here. So we only focus on the left and right. It's not up and down. So left and right, this is because of the centripetal assertion. This one because of the friction. Right, left and right only. So you can see the diagram there. Fc equals to friction. It didn't have any minus. So friction is nu mg. Because friction is nu plus with the mg over here, this one. There you have the value of the friction. Fc is mv squared over r or mr omega squared. So you can cancel out the m. So omega squared equals to nu g over r. Okay.
Okay.
So omega equals to square root of nu g over r. There you have how much is the fastest revolution per second before you can skip.
So FC static friction is what chapter?
Static friction.
FC.
FC is a centripetal force. FC centripetal force. It's not that static.
Oh, okay.
Okay, so centripetal force. Okay, we name it as FC. Yes, here. C. Usha, any question? Keshika, are you there actually?
No, sir.
Yes, sir.
Any question? Usha and
no.
No.
No, sir.
Actually, not very hard this chapter, right? It's either you so there are two types. One is horizontal circular motion. One is the vertical circular motion. That's it. Okay. Okay.
Okay, sir.
So I think next class for static, I think around 5. Can?
Today, sir. Okay, second, sir.
Yeah, around 5, okay.
Sir, 8 o'clock, sir.
8.
Yeah.
Let's see lah. I think I can do it. 8. Usha, Keshika, okay with that?
Yeah, 8 okay, sir.
8, okay.
Yes,
Okay.
sir.
Okay, we see it. Oh, we have
Okay,
we
sir.
start at 8. Okay, see you at 8 o'clock.
Okay, sir.
Okay,
Okay,
thank you,
sir.
sir.
Thanks, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Okay.